How to build a model steam engine. Stuart Models Victoria Part 4. Machining the flywheel. The first half of this took place in episode 3, and now it's down to business, down to the proper job of machining. Starting with drilling the hole through the centre of the flywheel boss. The front and side of this centre part of the flywheel has just been machined. And as usual, I started off with a centre drill, then I followed it through with a twist drill, and soon there will be a hole all the way through the centre of the flywheel. It's not the right size hole, but it's a hole nevertheless. This hole needs to be bored out to 7/16 of an inch in diameter. Some viewers have asked if I will leave the video running in real time, so you asked for it and here it is. This is a boring bar by name, and it's a boring bar by nature at the moment. It's going in there so slowly. Running the video at this normal speed will at least allow me to explain that I had to grind the boring bar to make it fit. It was too big for the hole. A 7/16 of an inch hole is very small. Why 7/16 of an inch? I really don't know. I think if I'd have designed this engine, I would have made it half an inch and had done with it. But no, it's 7/16 of an inch, not 8/16 of an inch. It's also worth mentioning that this is a carbide-tipped lathe tool, and you cannot grind these on an ordinary grinding wheel. You need what's called a green grit wheel. And I have one of these green wheels fitted to one side of my bench grinder. On the other side is a standard grey coloured wheel. Standard wheels are fine for high-speed steel, but once again you need a green grit wheel for a carbide tip cutter. These days I think I prefer the carbide tip tools to have replaceable tips, so when they go blunt you can just throw them away. And also you don't have to grind them, they're automatically at precisely the right angle to cut properly. Carbide tipped lathe tools are much more fragile than a high-speed steel lathe tool. There are pros and cons of using either of these type of tools. The good thing about carbide tipped tools is they are generally very sharp until you chip them, and they cut very well. High-speed steel tools are also very sharp, but they will soon blunt on cast iron if you take too hard and too fast a cut. You've probably noticed that I often clean up the casting before machining it, and this is a throwback to the days of using high-speed steel. I try and remove as much of the sand and scale, or the skin of the casting, as I can, because if you don't do that, the high-speed steel tool soon gets blunt with all the sand that's trapped in the outer layer. Normally for machining cast iron I would run the lathe in back gear, which slows it down. But in this case, because I'm boring a hole right through the centre, I can run the lathe at a faster speed. You can machine at a higher speed and a higher rate of feed nearer the centre of the work. I'm now getting quite close to the finished size, and this piece of steel I'm trying in place is the actual crankshaft that came with the kit. It's nearly there. I could actually press this on, but if I do that, the flywheel would then be permanently fixed to the shaft, and that's no good. It needs to be easily removable for assembly and disassembly. And this flywheel will be secured to the crankshaft with a single 2BA grub screw as shown on the drawing. This is the time I would get a little bit nervous, because if I take too big a cut, the flywheel is going to rattle on the crankshaft, and this is no good at all. This has to be a firm fit on the crankshaft, and I think the best way to describe the fit of a flywheel onto a crankshaft is firm, I suppose, which is not slack and not tight. The cutting tool is going through the centre of the hole very, very slowly, and the speed of rotation is quite fast for cast iron, but as I said, that's okay near the centre. And once the boring bar pops out of the other side, I'm going to reverse the direction of the traverse and not touch any of the controls on the lathe, just leave it as it is so that the boring bar comes back out the way it went in. And what this does is it just polishes the internal part of the hole. I would recommend buying some cast iron just to practice on before doing the job for real on the flywheel. Put a piece of cast iron bar in the chuck and drill a hole in the centre, and then using a boring bar, exactly like this, go back and forth down the centre of the hole that you've drilled until you get it to the size that you want it to be. There is no substitute for formal engineering training that unfortunately I never had. And when doing a job like this, you can fall back on your training and technique to do the job properly. And there's a good analogy with music, it's exactly the same. For instance, I had some classical training and I have a good technique. And so I fall back on that and the technique is still there. Maybe I don't really feel like playing, so I can just go on autopilot, but I have the technique and the skill to do it. And with engineering training, I do feel it's a very similar way. And at this point in the video, which has been running in real time for quite a while, I can hardly contain my excitement. Now the boring bar is coming out of the hole. And here's the big question. Is this hole the correct size to fit the crankshaft? It's time to stop the lathe and see whether the crankshaft fits in the hole. Oh no, the camera's gone off, I'll never know. Sorry about that, I was just messing about. And it fits perfectly. And I knew it would, because I've done quite a lot of this, but I do recommend the practice idea. Right, so the hole in the centre is great for the crankshaft. I can now carry on with the outside edge. But because the outside edge is held in the four jaws of the chuck, I can't go all the way down, I can only go about halfway down. In that last section I was beginning to drop off. I do like to accommodate the requests from viewers, but in future I will run in real time, but not for too long, not for as long as that. I couldn't go through that again. The voices have all started up and they're all arguing and shouting at each other at the same time. I'm going to take some medication. That's better, the voices have now gone away. So it's back to the job. Oh no, I'm still turning this flywheel. Attempting to be serious for just a moment. Turning a flywheel is quite a long drawn out process. You can't go too fast. If you do, you won't get a good finish. And if you're using high-speed steel, you blunt the tool. So you have to take it easy, particularly on the outer part of the flywheel. One major problem with small flywheels, I'll just cover this as a separate thing, is something known as chatter. Chatter is when the tool starts to cause harmonic ringing of the casting. And generally speaking, you only get this on the outside edge of the flywheel. In this clip, I'm finished machining the centre boss to the correct size. It has to be 1 inch through the centre. And to check this, I'm using a depth gauge on a pair of calipers. And the good news is, the centre hole is 1 inch deep exactly. And then it's back to the outer edge. This part of the video once again is running in real time. I'm taking quite a fine cut. I don't have auto crossfeed on this lathe, I'm winding the handle. But thankfully I do have power traverse, so on the outside edge I can just put it in auto feed. In this clip I've turned the flywheel round in the chuck so it's been held by the clean metal, and I'm now turning the other half of the outer part of the flywheel. The idea being to remove as much metal as possible because the rest of the operation will be done on a mandrel. And this is the mandrel that I'm making. I've refitted the 3-jaw chuck, so once this piece of steel is fitted in the 3-jaw chuck, I turn the mandrel to the exact size of the crankshaft. I'm using some oil to get a good finish, but I'm not getting a good finish, which means that the tool is blunt. But I'll continue to use it for the rough cuts, and here I've changed the tool tip for the fine cuts, and you can see how much better the finish is. You can't beat having a brand new tool tip on a carbide tip tool if you want the best possible finish. So after much fine cutting and a bit of sandpapering, I finally get the mandrel to precisely the size I want it to be. Not a tight fit and not a slack fit. A firm fit, just like the crankshaft. And now I'm coating it in Loctite 603. I always apply too much of this stuff, but anyway, the flywheel goes on, I rotate the flywheel to spread the Loctite 603 and then just leave it. I went into the house to make a cup of tea, brought the cup of tea back into the workshop, by which time the flywheel was fully cured to the shaft and I could continue the machining operation. The first thing to do though, as you've just seen, was I centre drilled the mandrel so I could support it with a live centre for turning these parts of the flywheel. Loctite 603 is amazing stuff. You wouldn't think that it would hold this thing so firmly so quickly. And so much so that within 10 minutes I'm turning the outside diameter of the flywheel to the right size. You can see now why I removed quite a lot of the material. I didn't want to stress out the mandrel and risk chatter. I've slowed the video down to real time, and you'll see now how slow the tool is advancing across the work. And the sound that it's making is quite a healthy noise, sort of a hissing noise. If it starts squeaking, that's chattering. And chattering can be caused by many factors. If the lathe is out of adjustment, if the headstock bearings are a bit loose, if the tool post is loose, if the tool is blunt, if it's the wrong kind of tool. There are many factors that can contribute towards this chattering. The main problem with flywheels are the spokes. You have a central hub that's held firmly in place, then you have thin spokes and quite a large mass of metal on the outside, which can easily set up a harmonic ring. Time now to go up to a faster speed, and the tool is advancing back across the work, and the finish is quite impressive. It's looking rather good. I'm quite pleased with this, and I'm especially pleased because there's not even a sign of chattering anywhere. So if you get chattering, how do you get away with it? Well, a couple of ways of doing it. You slow the lathe right down, as slow as it will go, and you take a very slow feed, and usually this will do the trick. But sometimes the best way to do it is to just speed up the lathe, remove the lathe tool from the proceedings altogether, and use some very coarse sandpaper to literally sand away the chatter marks. If you remember, I changed the tool tip on this tool for turning the mandrel. So I thought for the final cut across the work I would use this tool with its very fine, newly fitted carbide tip. And then, to avoid injury, I removed the tool from the tool post and put it on the shelf. And now I'm using different grades of sandpaper. I'm starting off with 80 grit sandpaper, which is fairly coarse, and I'm going to work down the grades. This is about 300 grit, and then I go down to 600 grit, which is wet to dry sandpaper. In this clip I've stopped the lathe and I'm cleaning up the inside edges of the flywheel because these are quite sharp. I can't do it with the lathe spinning. I'm using medium grade sandpaper to get rid of the sharp edges. I'm trying to make sure that I'm removing the sharp edges also from the square blocks that are cast into the flywheel. And now all I need to do is take the finished flywheel off the mandrel. And it's a bit of a fireworks display because there are a lot of iron filings around here. And it's a good job I've not been filing any aluminium at the same time as the cast iron, because a thermite reaction would take place and that would not be good, and it would make a mess of my vise. And here's the finished flywheel, and when I try it on the crankshaft it's a very good fit. It's also accurate, and it's cleaned up very well with the sandpaper by going down the grades. And to finish the job, all I need to do now is drill and tap this for the grub screw. I'm holding the flywheel in the vise at an angle. I go through first of all with a centre drill, followed by the tapping size drill, which is 5/32 of an inch, and then it's over to the bench to tap the hole by hand with a 2BA tap. A few viewers have been asking me why I don't use tapping compound or cutting compound, and the reason for this is you can't really see what I'm doing if the tap is covered in cutting compound. After tapping the 2BA hole, I fit the grub screw. And here's the flywheel resting up against the bed. So two of the major components are now out of the way. In the next episode, I will show how I machine the cylinder. Thanks for watching, and I hope you found it useful.